Hi everybody, the purpose of this video is to go over section 2.1, functions and graphs, well, namely functions. The chapter is functions and graphs, the section is functions. In this section we are going to talk about equations in two variables, what it means to be a function, talk about the functions when they are specified by an equation, and then we will talk about function notation. In a separate video we will talk about our application of profit-loss analysis. Okay, so let's get started. Here is an equation in two variables. Now here the two variables are x and y, and if the equation has the form ax plus by is equal to c, then as we know it has a straight line as a graph. However, if it is not a linear equation and it has certain powers here, then these equations are more difficult to graph because, well, they have a shape other than a straight line. So how do you plot them, or how do you sketch the graph? Well, you plot enough points to determine the total shape, and then you connect the dots. And we call this process point-by-point plotting. And here's an example. Here we want to sketch the graph of the equation y is equal to x cubed minus 2. And actually, it's already sketched for you right here. But before we do that, we actually have to produce some points. And here are the points that we want to produce. And these points are cleverly chosen to point out the shape of the graph. The first point is x is equal to 2, which is right here. And when x is equal to 2, y is going to be equal to 2 cubed, which is 8, minus 2, which is 6, which of course produces for us this point right here. The next one is going to, the next value for x we have is 1, and in that particular case y is going to be 1 cubed, which is just simply 1, or just simply 1, minus 2, which will be equal to negative 1, which of course produces this point here. When x is equal to 0, y is equal to 0 cubed, which is 0, minus 2, which of course gives us negative 2, as you can see here. And then finally for, well, not finally, but for y is equal to negative 1 cubed is negative 1, minus 2 gives us negative 3, as we can see on the graph. And then finally, if x is equal to negative 2, x cubed is negative 8. And then if you subtract 2 from that, we get negative 10, which you can't see because we only go down to 6, but it's somewhere down here. Okay, so once you've done that, then you can connect the dots, which you can see right here, and this would be the graph for this particular cubic equation. Now, when you have to do this for your homework, though, you are going to be doing it in MML. So let's see how we would actually plot that for the case of MML. Well, here's our graph. Okay, the first thing you're probably going to do is make this graph as big as possible. Once again, you can click on this, but it will only produce for you a graph of a certain size. You can't make it bigger here. We can make it as big as the window allows. So there we go. I can't get much bigger than that. Then to plot a cubic, you want to use this point right here, the 4-point cubic tool. Okay, click on that. And now, and also with your 4 points, you actually want to make sure those 4 points include the saddle point area. So what I'm going to do is I'm going to click the value for x is equal to 1, that is 1, negative 1, which would be right there. I'm going to click the value for 0, which should be 0, negative 2. I'm going to click the value for negative 1, which would be this point right here. And now I'm going to go click the value for either x equals to 2, which would give me 6, or I can click the value for x equals negative 2, which will give me negative 10. Since we actually were able to plot 6 on the last one, let me go ahead and click that one. So you would click this, and that is the shape of the graph that you want. And you can see that's sort of right because it is crossing negative 10 right there. So when you see your problem, and you will, to plot a cubic function, this is how you will do it. You will use the 4-point cubic tool. You will plot your 4 points. Make sure 3 of the 4 points are in what we call the saddle area, which is right here. And once you've done that, you can click check answer and you will be good to go. Okay, now we want to talk about correspondences and relations. The book talks a lot about correspondences. In previous classes, you've heard a lot about relations. And remember, a relation is just simply a set of ordered pairs. The first element belongs to one set. We kind of call that the input set. And the second element belongs to another set, which we tend to call the image set. Sometimes they both belong to the exact same set. In this particular case, it's typically the real line, particularly if the relation is expressed as an equation. What is correspondence? It's just basically another way of saying relation, however it's just in a different context. Typically correspondence is used in more of a real world context, whereas relation is basically a mathematical definition. An example of correspondences, well, you see some here, and there are also some in your notes. And one is, well, for each pitcher, there corresponds an ERA. For every pitcher, we'll have a ERA, which is unique to that pitcher. It might be same for two pitchers, but still each pitcher will have an ERA. They also might have a strikeout per game record, or something like that. To each wide receiver, there corresponds, among other parameters, the average yards after a catch. And then to each volleyball player, there might be there might be a correspondence to, among other things, the number of kills per match. Now, once these correspondences are defined, and they could be defined using an equation, they could just be defined using a mapping, just an arbitrary mapping between the input, which would be a volleyball player, and the output, skills per match. I don't think there would be an equation that could define that for each volleyball player. But once they are defined, and however they are defined, one can make predictions and also decisions based upon those relations. Okay, well then what is a function? Well, a function is a correspondence or a relation that has exactly one output for every single input. If your input produces two possible outputs, then it is not a function. It is just simply a correspondence or relation, but is not a function. And of course, this brings us to our first definition for this section, and that is that of a mathematical function. And simply, a function is a correspondence between two sets, such that each element in the first set corresponds to one and only one element in the second set. Of course, the first set, which is the input, we call the domain of the function. The second set, which is the range, the second set, which is the output, we call the range of the function. And of course, when all this occurs, we mathematicians like to say that a function is a relation or a correspondence that is well defined. Function specified equations. Well, in this course, most of the functions that you're going to be dealing with will be specified by some sort of an equation. If that's the case, then the domain and the range will always be a subset of the real line, any possible number between negative infinity and infinity. The value associated with the domain will be the value associated with the domain or the input we will call the independent variable. The value associated with the range we will call the dependent variable. So basically, the range will always be dependent upon the domain. And this brings us to our second definition, which is basically what we stated before. If you have an equation in two variables, and if we get exactly one output for each input, then that equation specifies a function. The graph of such a function is the graph of the specifying equation. And if there is more than one output for a given input, then obviously that equation does not specify a function. And then here's our third definition, and this is the definition of a graph of a function. Some people think that a graph is that cute little picture that you draw. Actually, it is not. The graph of a function is actually a set, and it's a set of all points x and y on the Cartesian plane that satisfies a function. So what does that mean? Well, that the graph of y equals x squared is basically nothing more than the set of this coordinate, where the first coordinate is x, the second coordinate is just the square of x for all values of x between negative infinity and infinity. Now, the graph that you see when you plot that is actually a visualization of this particular graph, but in the strict mathematical sense, a graph is really nothing more than a set, and the image that you see on the Cartesian plane is actually just a visualization of that graph. Okay, and this brings us to one of the examples that you will have to deal with in your homework, and that is to determine if certain equations specifies a function or not. And here we're going to basically decide that the independent variable is x. Okay, so how can we figure this out? Well, if the independent variable is x, that means that the dependent variable is y, and we would need to solve for y. And we can do that by adding x to the fourth to both sides, and if we do, we will have that y squared is equal to x to the fourth plus 9. All right, then we're going to want to take the square root of both sides. And if we do, we will have that y is equal to plus or minus the square root of x to the fourth plus 9. Okay, well, that basically means that y can either be equal to the square root of x to the fourth plus 9, or y is equal to the negative square root of x to the fourth plus 9. And as a consequence, since the same value of x can produce for you two different values of y, this is not a function. Let me show you an example. Suppose that x is equal to 2. Okay, well, if that's the case, x to the fourth is equal to 16. 2 times 2 times 2 times 2, yeah, that's 16. And then x to the fourth plus 9 is equal to 25. And of course, the square root of all this would be equal to plus or minus 5. All right, so if x is equal to 2, then y can be equal either to the square root of x2 to the fourth plus 9, which is equal to 5, or y can be equal to negative the square root of 2 to the fourth plus 9, which is negative 5. So for one value of x, we have two values of y. This cannot be a function. Okay, and this brings us to our very first theorem, and that theorem is the vertical line test. And you guys have seen this before, but we're going to run through it real quick. An equation specifies a function if each vertical line in the coordinate system passes through at most one point on the graph of the equation. If it passes through two or more points on the graph of the equation, then that equation does not specify a function. Okay, so here, even though this graph specifies a function, here's my vertical line, it crosses through one point. If I move this vertical line, it will still cross through only one point. Even though even here, even though the function is getting steeper and steeper, it is not coming completely vertical, so this vertical line will pass through only one point. So this right here is a function. However, over here, this is clearly not a function. At this particular point, it only takes one position of the vertical line for it to fail. It passes through the graph 1, 2, 3, 4 times. So this right here fails the vertical line test and is not a function. And of course, we can have a few examples here. Does this graph represent a function? The answer is no. I can draw a vertical line right here. Well, sort of a vertical line, sorry about that. And as you can see, it passes through 1, 2, 3 points, not a function. So the answer here would be no. What about this graph? Well, this graph actually does indeed represent a function. Actually, this is the function f of x is equal to what we call the cosine of x, which you would learn if you took pre-calculus. But notice, if I move this line anywhere on this graph, it will only intersect the graph at one particular point. So this does indeed represent a function. Okay, what else do we want to talk about? Oh yes, domain and range. If a function is specified by an equation and the domain is not indicated, then the domain is the set of all real numbers for which this function is defined. If the function is not defined for a particular value or a particular collection of values, then that value is not part of the domain. And here is a trivial example. Here is y is equal to 1 over x. Okay, or we can say that this is f of x is equal to 1 over x. Notice that this function is not defined when x is equal to 0. As a consequence, x is not part of the domain. And we can show that by saying that the domain is equal to the open interval from negative infinity to 0, not including 0, unioned with the open interval from 0 to infinity. So that would be the domain in interval notation. Notice that it does not include 0. Or you could say that the domain is equal to all values of x such that x is not equal to 0. And that brings us to this particular example here. We want to find the domain of the following equation, assuming that the x is the independent variable. Now notice that we are operating on the real line. We are not operating on the complex plane. So y is only, so the square root of any function is only defined when its argument is greater than or equal to 0. So this function is only defined when the argument right here, x minus 2, is greater than or equal to 0. Okay? Well, that can only occur when x is greater than or equal to 2. As a consequence, y is only defined when x is greater than or equal to 2. So the domain will be equal all values of x greater than or equal to 2, just like that. And in interval notation, we will write that as the half open interval from 2, including 2, all the way up to infinity. For any values that are less than 2, this will produce for you a negative number, and we cannot, and if we are restricting ourselves to the real line, the square root of any negative number is not defined. One of the collection of homework problems that you're going to find are problems where you actually have to classify a function into these 3 classes. Okay, so here we have an equation that specifies a function, and this is kind of crazy. We have that x is equal to 1/4 y minus 8, where the independent variable is x. Okay, and we want to determine if this function is linear, constant, or neither. Well, check this out. If this is the independent variable and this is the y and this is the dependent variable, then we actually need to rewrite this so that it is of the form y is equal to some slope times x plus some other number. So we need to solve for y. Now to do that, we are going to multiply both sides by 4. And if we do, we will have that 4x is equal to, well, 4 times 1/4, that's just going to be 1, so that's going to be equal to y, minus 4 times 8, which is 32. Okay, now I want to add 32 to both sides. And I'm going to do this up here, and then these will cancel, and I will then have y is equal to 4x plus 32. Now why did I do this? Well, because x is the independent variable, which means that's the input, y must be the output. So we want to write this as the output in terms of the input, just like this. Okay, so now we can take a look at our options. Is this function a constant function? The answer is no. This is a linear function because it's in slope-intercept form. So this is out. Does this function specify neither a linear or a constant term? Well, no, we actually have it right here in slope-intercept form. So B has to be the answer. It can't be C. Of course, there's more to do. We have it in the form y is equal to mx plus b. So in this particular case, m is equal to 4 and b is equal to 32. Now let's talk about function notation. Function notation allows us to, one, assign a name to the function, usually something clever like, well, I don't know, f or g, and then identify which variable or collection of variables is an independent variable. Yes, you can actually have more than one variable that defines a function. We call those multivariate functions. So here, consider what we have here. We have y, the equation y is equal to x squared minus 2x plus 1. This does identify a function. It's a parabola. And to put this in function notation, we just simply replace y with f of x, where once again f is the name of the function and x specifies what the independent variable is. If there are other letters in here that aren't specified in here, well then those letters are basically parameters, not the independent variable. Now this notation is what we call function notation, and this can be read as a number of ways. One is f of x, the function f of x is equal to this, or is defined as that. F evaluated at x is equal to this, whatever, x squared minus 2x plus 1, or the value of f at x is once again equal to this. So there's a variety of ways to read this. The most common way is, though, f of x, the function f of x is defined as x squared minus 2x plus 1. Okay, one of the things that you're going to be doing in this section is evaluating functions. And here we are. Here we have the function. We are going to call it f. The independent variable is x, and this is defined as 4 times x minus 5. And we want to evaluate the function f when x is equal to 10. That's what f of 10 means. Okay, well in that case we are going to replace x with 10. And then we will have, and then where we see an x we will have a 10. Remember, this is 4 times x, so when we replace it we're going to have 4 times 10. So we will have that f of 10 is equal to 4, replacing x times 10 minus 5, which of course is going to be 40 minus 5, which is 35. Now for the second part here, we have the problem, if f of x is equal to 19, what is the value of x? So here they're telling us that f of x is going to be equal to 19. So we can substitute 19 for f of x, or we can replace f of x with 19. Okay, and then if we do, we will have that 19 is equal to 4x minus 5. I can add 5 to both sides of the equation. And when I add, these will cancel. I will have 24 is equal to 4x. I can divide both sides by 4. And if I do, I will have that 6 is equal to x, because these cancel, and 24 divided by 4 is 6. And I can turn that around and just simply say that x is equal to 6, and that would be the answer to that particular problem. Now the other way you might evaluate functions is not with the equation itself, but with a graph of the equation, and that's what we have here. Now here we want to evaluate f of 2. That's basically evaluating f of x when x is equal to 2. Now in this graph, of course, the abscissa right here corresponds to x. The ordinate, or the vertical axis, corresponds to y is equal to f of x. Okay, so if x is equal to 2, and that puts us here. Okay, then we walk up until we intersect the graph. That puts us right there. And of course, when x is equal to 2, f of x is equal to 2. So we will have that f of x is equal to 2. Now, for the second part, we have that f of x is equal to 6. So we're up here. We want to find what values of x is f of x equal to 6, and there may be more than one answer. So here we are at 6. We go to where 6 intersects the graph. That occurs here, and that occurs when x is equal to negative 3. So in this particular case, x will be equal to negative 3. Now in your homework, you might find that there'll be more than one value of x more than one value of x that satisfies the given problem. For example, maybe in your homework they'll ask for what values of x is f of x equal to 1. In that case, you'll be here, and there will be 3 values. One will be negative 2.5. The other one will be, actually that's probably negative 2.5. This one would be positive 0.3. And this one would probably be 2.2. There would actually be 3 values which you would need to put in, probably separated by a comma. Okay, then the next class of functions you will have is to find the domain. Now notice here nothing is specified. Here the domain is all real numbers except that number for which the equation is undefined. All right? Well, notice here f of x is undefined whenever the denominator is equal to 0. Of course, and that occurs when x plus 9 is equal to 0, or when x is equal to negative 9. So the domain for f are all values of x with the exception of this one. And how would you write that? Well, there's a couple of ways. One way in set builder notation would be that the domain is equal to all values of x, and I think that such that x is not equal to negative 9, And then in interval notation, that would be the open interval from -infinity to -9. So parentheses, unioned with the open interval from -9 to infinity. And notice that the union of these two intervals includes every single point on the real line except -9. And this brings me to my last problem for this video, or last example. In here, we want to define f of x, which is equal to x, or we want to evaluate f of x, which is defined as x squared minus 4x plus 9, when for the case where the argument is equal to 6x. So what do? Well, wherever we see an x, we replace it with 6x. So this will be equal to 6x squared minus 4 times, instead of x, 6x, plus 9. So if our function is defined like this, we will replace x with whatever is in the argument here, which is essentially what we did. Then once we evaluate that, we are going to have that f of 6x, look that more like the parenthesis, that is going to be 6x squared, which is just 36x squared, minus 4 times 6x, which would be minus 24x, plus 9. And there you go. And that is all I have for this particular video. There will be another video that goes through the applications which you will have in your homework, and be on the lookout for that. Nonetheless, if you have any questions, please feel free to contact me. This is Bob Boyle, signing off.